On August 10, 1628, the Pride of the Swedish Empire cast off her lines in Stockholm harbor. She was among the most expensive and heavily armed warships Sweden had yet built. She carried 64 bronze cannons. She displaced around 1,200 tons. Her name was Vasa. The launch was not a combat operation, it was a celebration. The weather was clear and the wind was gentle. The ship had sailed less than 1 nautical mile when a light gust of wind caught her sails. A harmless gust, something a seaworthy hull would answer with a lazy roll. But Vasa did not shrug it off. She heeled over to port and stayed there. The inclination increased. The physics of the hull reached a catastrophic tipping point. The lower gunports were open to allow a salute to the crowd. These openings sat dangerously close to the waterline. As the ship leaned, the sea poured in over the sills. In seconds, the vessel transitioned from a surface combatant to a sinking stone. She went down with sails set and flags flying. She settled upright on the harbor floor 105 feet below the surface. The entire voyage had lasted about a quarter of an hour. The disaster was immediate. Many escaped into the harbor, but around 30 people are believed to have died. It was not caused by enemy fire or navigational error. It was caused by a fundamental failure of engineering geometry. The ship was a floating contradiction. She carried an enormous weight of artillery on her upper decks, but she lacked the counterweight below the waterline to keep her upright. The ballast deep in her hold weighed only 120 tons. It was not enough to offset the center of gravity, which sat dangerously high. The ship was top-heavy. She was unstable before she even left the dock. The investigation that followed was chaos. No single person could be blamed because the king himself had approved the dimensions, but the wreckage left behind a forensic puzzle. Modern archaeology has uncovered strange discrepancies in the hull construction. Workmen on the port side and workmen on the starboard side appear to have used different rulers. One team used a Swedish foot. The other team appears to have used a Dutch standard that was slightly shorter. This may not have sunk the ship on its own, but it reveals the chaotic lack of standardization in the shipyard. The Vasa was a prototype built without a proven blueprint. The water in Stockholm harbor is cold and brackish. It lacks the salt content of the open ocean. When Vasa hit the bottom, she did not break apart. She sank into the stiff clay and mud and settled upright. In that cold, brackish dark, the harbor sealed her away. In most oceans, a wooden ship is devoured by shipworms within decades. These organisms eat the cellulose until the timber dissolves into dust. But here, the brackish water was hostile to shipworm. Vasa was not eaten, she was entombed. For the people of the 17th century, the loss was a national trauma. But for the historian of the future, it was an accidental gift. The mud sealed the lower hull. The lack of oxygen preserved the oak. The ship became a perfect time capsule waiting for a technology that would not exist for another 300 years. Most of the bronze guns were recovered by divers in the decades after the sinking, but carriages, rigging, and countless artifacts remained. Human remains were also found within the wreck. The memory of the location faded. The surface of the harbor returned to normal traffic. Anchors from other ships dragged over the site and tore away the upper masts, but the hull remained hidden. The city of Stockholm grew around the grave. Industrial waste and harbor silt rained down for centuries, covering the wreck in a protective blanket of grime. By the 20th century, the exact spot of the Vasa had faded from public memory. Some said she was in the deep channel. Some said she had been destroyed. The ship had vanished from the map, but she had not vanished from the physical world. She was waiting in the dark far below, held fast by the suction of the clay. The mystery endured. In 1956, a fuel engineer and amateur archaeologist named Anders Franzén began a systematic search. He was not looking for gold. He was looking for a specific biological boundary. For years, he dragged grappling hooks and pulled up seabed samples, coming up empty every time. The harbor floor was a junkyard. Bicycles, old stoves, discarded timber, anything but Vasa. Franzén changed his tactic. He built a core sampler. It was a simple, heavy lead weight, with a hollow steel tube at the bottom. It was designed to punch into the seabed and bring up a plug of material. He spent days drifting over the suspected coordinates, dropping the probe like a spear. On August 25, 1956, the probe slammed into an obstruction. When Franzén winched it back to the surface, the steel tube was not filled with mud. It was plugged with a solid cylinder of black oak. He had cored the hull of the Vasa. The wood was 333 years old, but it was as hard as the day it was cut. Finding the ship was only the first variable in the equation. To raise her without rolling her over, the team had to understand the same instability that sank her. Naval architects call it metacentric height, the working gap between the ship's center of gravity and the metacenter, the point defined by how buoyancy shifts as the hull heels. In a stable vessel, wind pushes the hull over, buoyancy slides outward, and a lever arm forms that drives the ship back upright. On Vasa, the upper deck bronze guns forced the center of gravity so high that the righting lever arm was almost zero. When the wind leaned her, she had nothing to push back with. The geometry of the hull had doomed her. She was chemically unstable, and that had to be accounted for before the lift began. Now the engineers faced a new physical enemy. On paper, she was a 1,200-ton displacement, but the effective load was much higher. The hull was glued to the seabed by mud suction. The clay of the harbor floor had gripped the timber for centuries. If a crane simply grabbed the ship and pulled the hull, would likely tear apart. The suction could be enormous. To break this seal, they could not pull from above. They had to attack from below. At 105 feet, the environment is hostile to human life. The water is close to freezing, thick with silt, and a diver often meets the wreck by impact rather than sight. Masked to planking, in the dark, the Vasa loomed as a wall of oak, preserved and yet imprisoned by the geology. To lift her, they would have to violate the seabed itself and excavate beneath the hull. The problem was brutal in its simplicity. The lifting cables had to pass beneath a hull pressed hard into clay. There was no clearance, and any trench collapsed as fast as it was cut. Push too aggressively, and the wreck could settle deeper, roll, or break. What they needed was a way to carve the seabed without ever striking the ship. The job fell to the Swedish Navy and their chief diver, Per Edvin Felting. Felting was a master of underwater operations. He understood that a human diver is a soft organism in a hard environment. He led a team that would perform one of the most dangerous construction projects in maritime history. They had to bore 6 tunnels completely through the clay directly under the keel of the ship. They were not drilling through rock, they were drilling through a dense, sticky matrix of clay and centuries of harbor trash. To cut the tunnels, the divers used a specialized tool called the Zetterström nozzle. It was a high-pressure water jet paired with dredging suction. When the jet hit the clay, it did not just wet it, it disintegrated it. The sediment became a slurry, which was then sucked away by a separate hose. It was an excavation system that used water as a blade. The physics of the nozzle created a severe tactical problem for the diver. Newton's third law states that for every action there is an equal and opposite reaction. When the nozzle fired a jet of water forward with massive force, it created a recoil that kicked the diver backward. This was not a gentle push. It was a violent thrust that could slam the operator into the debris field. The diver had to fight the recoil, constantly bracing his boots against the mud to stay in position. The working conditions were nightmarish. As soon as the jet hit the clay, the visibility dropped from poor to zero. The water filled with a dense cloud of suspended sediment. The divers were blind. They were working entirely by touch, deep inside a narrow tunnel beneath a rotting warship. They were alone in the dark with a high-pressure hose and a suction pipe. They had to feel the difference between the clay they were cutting and the black oak of the hull. One mistake could slice into the ship or trigger a collapse that would bury the diver alive. For 2 years, the team worked in these conditions. They executed 1,300 dives without a single fatal accident. It was a triumph of discipline over probability. They carved 6 perfect tunnels through the harbor floor. Once a tunnel was complete, a lead line went through first, followed by a heavy steel lifting cable, the thick wire that would become the straps of the cradle. By 1959, the trap was set. The Vasa was no longer glued to the bottom. She was sitting in a basket of steel wire. The divers had done the impossible. They had prepared the load. Now the engineers had to figure out how to lift it. The cables were strong enough, but no crane in the world had the leverage to pull the ship straight up without breaking her spine. The lift would require a different kind of engine. The cables were in place, but the physics of the lift remained a lethal puzzle. The Vasa was not a block of steel. She was a wooden skeleton, held together by rusted iron bolts and wet rot. If the engineers applied too much force at a single point, the hull would shear in half. A standard crane was useless. The dynamic loading of a crane swinging in the wind would snap the fragile timber. The lift had to be perfectly vertical and perfectly smooth. In the planning phase, the salvage committee had been bombarded with ideas that ranged from the ingenious to the absurd. One proposal suggested filling the entire hull with millions of ping-pong balls. The theory was that the collective buoyancy of the air inside the balls would float the ship to the surface. It was a charming idea, but it ignored the laws of pressure. At 100 feet down, the hydrostatic pressure is roughly 45 pounds per square inch. The ping-pong balls would have been crushed into plastic discs long before they could generate any lift. The engineers rejected the fantasy and chose a method based on heavy industrial logic. They employed two massive salvage pontoons named Oden and Frigg. These were not simple barges. They were floating platforms designed to manipulate the laws of displacement. The plan was to use the water itself as the engine. The technique was a hydraulic pontoon lift. It is a slow and deliberate cycle that trades speed for control. The process begins by flooding the tanks inside the pontoons with water. As the pontoons take on weight, they settle lower into the sea. Once they are low enough, the 6 steel cables running under the Vasa are pulled tight and locked onto the decks of the pontoons. The system is now a single tension unit. Then the cycle reverses. Powerful pumps begin to empty the water from the pontoons. As the weight of the water leaves the tanks, the pontoons regain their buoyancy. They want to rise, but they are tethered to the wreck below. As the pontoons fight to return to the surface, they exert a massive, controlled upward force on the cables. The Vasa is lifted not by a machine, but by the displacement of the ocean. This method does not bring the ship to the surface in one motion. It is an underwater elevator that moves one floor at a time. The pontoons would lift the ship a little less than a meter off the bottom. Then tugboats would tow the entire assembly, pontoons, cables, and the submerged wreck, into slightly shallower water until the Vasa grounded again. Then the divers would descend. They would slacken the cables. The pontoons would be flooded again to reset the height. The cables would be tightened. The water would be pumped out, and the ship would rise another little less than a meter. The operation required 18 separate lifts. It was a tedious architectural crawl. With every step, the Vasa moved from the deep clay of the harbor center toward the protection of the shallows. The water pressure decreased. The light increased. The ship was traveling up the slope of the seabed like a climber ascending a mountain in the dark. By the end of the operation, the ship was resting in water that was only 50 feet deep. She was no longer a deep sea wreck. She was a hazard to navigation sitting just below the surface. The easy part was over. The buoyancy lift had done its job of transport, but to bring her into the air required a final transition that physics does not forgive. The team had to break the surface tension and expose the wood to an atmosphere it had not seen since the reign of King Gustavus Adolphus. On the morning of April 24, 1961, the salvage operation entered its terminal phase. The Vasa was resting in 50 feet of water just off the island of Kastelholmen. The long pontoon crawl was over. Vasa now waited just beneath the surface world. But the final vertical pull remained. This was the most critical mechanical window in the entire project. The interface between water and air is a zone of chaotic energy. Waves wind and the loss of buoyancy support all conspire to destroy a fragile structure. The engineers could no longer rely on the coarse power of flooding and pumping the pontoons. The tidal method was too imprecise for the final inch. If the ship rose too fast, she might break her back. If she rose unevenly, the shift in weight could snap the cables. To control this transition, the team switched to hydraulic jacks mounted on the decks of the pontoons Oden and Frigg. These jacks allowed the operators to pull the cables millimeter by millimeter. The lift was no longer a transport mission, it was a surgical extraction. In the years leading up to this moment, the planning committee had debated how to protect the hull during this transition. One of the more radical proposals became known as the ice cube method. Proponents suggested building a cofferdam around the wreck and freezing the water into a solid block of ice. The theory was that the ice would encase the timber and support every inch of the structure during the lift. The ship would rise as a frozen monolith. The plan was rejected due to the exorbitant cost of refrigeration and the sheer thermal impossibility of freezing that volume of water. Instead, they trusted the hydraulic jacks and the strength of the oak itself. At 9:03 in the morning, the hydraulic pumps engaged. The cables tightened. The water in the harbor was calm. Slowly, the shape of the wreck began to separate from the dark water. The first pieces to break the surface were not the masts. They were the tops of the vertical stanchions on the bulwarks. Then came the upper rail. The wood was black and ancient, but it held its form. As the hull rose higher, the true nature of the ship was revealed. It was not a rotting hulk. It was a floating art gallery. The mud had preserved the intricate Baroque carvings that adorned the stern. Wooden warriors' lions and Roman emperors emerged from the water dripping with silt. They had been carved in the 17th century to terrify the enemies of Sweden. Now they were staring at a television audience of millions. But the engineering test was not over. The ship was still full of water and mud. She was effectively a heavy container hanging from the pontoons. To prove she was a ship and not just debris, she had to float on her own keel. The pumps were lowered into the hull. They began to discharge thousands of gallons of water per minute. The salvage team watched the draft marks. As the internal water level dropped, the hull became lighter. The strain on the hydraulic jacks decreased. Slowly, the Vasa began to lift herself. The buoyancy returned. For the first time in 333 years, the ship was supporting her own weight. The cables went slack. The pontoons were no longer holding her up. The operation was a definitive success. The ship had been returned to the element she was built for. But as the water drained away, the timber was exposed to the air. The chemical clock had started ticking. The salvage was over, but the battle for survival had just changed its terms. The raising of the Vasa was a victory for mechanical engineering, but it created an immediate crisis for chemical engineering. The ship had spent more than 3 centuries submerged in water. Every cell of the oak timber was saturated. The water was acting as a structural filler, keeping the cell walls from collapsing. If the wood was allowed to dry out naturally, the water would evaporate and the cells would collapse. The hull would shrink, crack, and warp until it began to tear itself apart. The ship would survive the ocean only to be destroyed by the air. To prevent this, the conservation team launched a preservation campaign that would last 17 years. They could not save the wood by keeping it wet with water. They had to replace the water with something that could support the structure. The solution was a waxy petroleum-derived compound called polyethylene glycol. This substance has a unique property. It is soluble in water, but when it dries, it hardens into a solid wax. The process was a slow-motion transfusion. The hull was housed in a temporary aluminum structure and subjected to a constant mist of the chemical. Day and night for nearly 2 decades, the sprayers coated the ancient black oak. The polyethylene glycol slowly soaked into the timber, gradually displacing the water. It penetrated the cellular structure and hardened inside the microscopic walls of the wood. When the spraying finally stopped, the water was gone, but the shape remained. The Vasa was no longer just wood. She was a hybrid material of oak and polymer. This chemical intervention saved the ship. Today, the Vasa stands in a dedicated museum in Stockholm. She is 98% original. The carvings that were pulled from the mud are back in their places. The lower gunports that once dipped below the waterline are permanently open, but now they overlook a climate-controlled gallery rather than the harbor floor. The recovery of the Vasa rewrote the rulebook for marine archaeology. It proved that a total salvage of a large wooden vessel was possible. It turned a catastrophic military failure into a triumphant historical asset. The ship that was meant to dominate the Baltic Sea for the Swedish Empire ended up serving a different purpose entirely. She became a time machine. The irony of the Vasa is in her timeline. She was built to fight wars, but she never fired a shot in anger. She was designed to be the pride of the fleet, a symbol of Swedish power, but she never completed a single voyage. She was a disaster in 1628, but she is a miracle in the modern era. If she had been a successful ship, she would have fought in the 30 Years' War and likely been destroyed or scrapped for firewood when she grew old. Because she failed so quickly and so completely, she was preserved forever. The salvage operation of 1961 was not just about lifting a heavy object. It was about reversing the arrow of entropy. The engineers and divers who worked in the dark, freezing mud of Stockholm Harbor did not just recover a ship. They recovered a lost century. The Vasa stands today not as a monument to naval power, but as a monument to the stubborn ingenuity of the human desire to remember.